This is problem number 2 in the extras section. Test 4 extras, problem 2. What is the velocity of sound in a train track that is made of steel with density of 7,850 kilogram per cubic meter? Let's say you hear the train by first putting your ear on the steel track and then get up and hear it 1.8 seconds later in the air. How far away is the train? So I'm kind of making this like a good old Western movie where you're a train robber. You put your ear on the steel train tracks, you hear the train, and you get up, and a little bit later you hear it in the air. Since the velocity of sound in steel is quicker, it will come to you first, then it will take it a little bit of time to come to you through the air. From there you can calculate what is the distance to the train. Assume the temperature in the air is 25 Celsius. If a typical train travels at 15 meters per second, how long will it take the train to arrive? Therefore, that's the time that it takes for you to get ready with your team to rob the train. Okay? So let's see here how to calculate this. Well, we first have to use the velocity of sound in a solid is equal to square root of the Young's modulus divided by the density of the solid. This is the same reasoning goes true with this as with liquid. So I'm not going to explain the reasoning. The top has to do with the inelasticity of the solid, so some elastic property, and then the bottom is the inertial property of the solid, and it ends up that it's the same units, and it comes out to be meters per second. Okay, so this is known as Young's modulus. So let's use the Young's modulus for steel. Young's modulus for steel. Let's write it here. Young's modulus for steel is 200 gigapascals. If you want to know the Young's modulus for other materials, for aluminum, it would be 70 gigapascals. Young's modulus for aluminum, 70 gigapascal. So aluminum is easier to bend than steel. Steel is more inelastic. Okay? So 200 gigapascals. So you put that here. 200 times 10 to the 9th. And then the density of steel is given to you, 7850. And the units, I don't have to work it out again. Like the previous problem, it comes out to be units of meter per second. So 5,047.54 meters per second. So remember, the velocity of sound in seawater was roughly around 1,400, 1,500. This one is about 3 or 4 times faster than that. Velocity of sound in a solid is much quicker than even in a liquid and even in air. Okay? Now, what would be the velocity of sound in air? Well, it's saying assume the temperature is 25 Celsius. So the velocity of sound in air, 331, 1 plus t over 273 to the 1/2 power. I've shown that equation before and I've done problems with that. So all I'm going to do is now take 25, put it in there, and quickly calculate the velocity of sound in the air. 1, it's going to come out to be 345.82 meters per second. Okay, so now here's what's going to happen. So let's visualize this. So if the train is here, okay, and it's giving out the sound wave through the steel tracks, okay, the distance is a certain distance away, that's equal to the velocity of sound times t. The time, we don't know how long. How long is it going to take for the sound wave to reach you? Okay, here you are, you put your ear on the steel tracks, okay, so the time that it takes, we don't know, but we can solve for it. The distance, we don't know either. So we have the distance is, the velocity of sound, we found 5,047.54. 5,047.54 t. Okay? Then you get up, and 1.8 seconds later, you hear the velocity of sound that it made towards you, right? So not only was the velocity coming through the steel, it was also coming through the air, right? So you get up, and you have the distance d equals velocity of sound in air times t plus 1.8, right? We don't know how long it took the sound to travel through the steel tracks, but we do know that it took 1.8 seconds more to travel through the air, right? So we say t plus 1.8, the velocity of sound in air, 345.82. So d is equal to 345.82 t plus 1.8. The two are equal to each other. So this must be equal to 5047.54 t. So I can multiply this in. So I have 5047.54 t, 345.82 t plus, multiply that by that, 7.54 minus 345.82, 4701.72, t is equal to 622.476, therefore t is equal to, so that means originally the velocity, the sound wave that came to you from the train through the train tracks, it took you 0.13239 seconds to reach you. Okay, through the air it took you 1.8 seconds later, so this is through the tracks. Through the air, it took 1.8 seconds more than that. So what would that give you? 1.8 more than that, that would give you 1.93239 seconds to get to you. So it took about 2 seconds to get through the air, and it took about 0.1 something seconds to get through you through the train tracks. So how far away is the train? We can now put this t here, 0.13239, into this equation, 5047. So you have distance d is equal to 5047.54 times 0.13239. Since each meter is about 3 feet, that's roughly about 2,000 feet away. Okay, that's how long the train is from you, 2,000 feet. Okay, now you could have also done it this way. You could take the distance, you could say it's equal to the velocity of sound in the air, 345.82, times the time that it took the sound to reach you through the air, 1.93239, and that should give you the same answer, 345.82 times 1.93239, you get 668.26 meters, okay? Same answer. So this is basically how robbers used to do it. Well, of course, without all these calculations and stuff, but they sort of had a feel for it in the Western days, right? They got up, they heard the velocity of sound in air, and then they could kind of figure out how far away the train was from there. Well, if the train is going at 15 meters per second, how long is it going to take to get to you? So distance is equal to velocity times t. Well, since the distance is 668.26, if the train is traveling at 15 meters per second, so so you have less than a minute, roughly about 45 seconds to get ready to go rob that train or bomb that train or whatever you are going to do, okay? So basically the idea of this is the farther away the train is, the bigger the time interval between you hearing it through the steel track and you getting up and hearing it through the air. For example, what would have happened if you got up and you heard the sound 2.8 seconds later? So instead of 1.8, it was 2.8. What would that do? How would that change it? Well, that would make this 2.8 times 345, 2.296. And then what would that, how would that change things? Then you do this and you get the same answer. 4701.72 t is equal to 968.296, and the t would be so that means the train was much farther away. It took 0.20 seconds for the sound to travel to you through the train tracks. So then what was the distance? It would be 5,047.54 times 0.2059, 0.8 seconds. It would be 1,039, whereas right now it was 668. So roughly speaking, what is that? That's about 400 meters more if it took an extra second. And then if it took one more second after that, 3.8 seconds, roughly maybe it's going to be about 1,400 meters away. Okay, so you can kind of see the pattern there. The bigger the time interval difference to hear something from the solid versus from air, the farther away that object is. Okay, so you can see how to do these kinds of problems. Thank you.